Welcome, we're group number 7 from section 1, and today we'll be presenting our second lab practice called viscosity reduction of crude oil. In order to present our lab practice, we divided our presentation in several sections, which are introduction, methodology, results and discussion, and finally, we'll be presenting our conclusions.
Nowadays, oil plays a crucial role in people's daily lives and in the industry, being the main engine of the world economy. This fossil energy source has become the most widely used resource to power industrial machinery, transportation, and the production of electrical energy. It is so important that the global demand for crude oil has been intensified steadily over the past 20 years. Consequently, heavy crude oil has drawn the attention of the oil and gas industries due to its vast reserves. However, because of the high percentage of heteroatoms like nitrogen, oxygen, and sulfur, metals like vanadium and nickel, and asphaltenes, the crude oil is very dense and has an elevated viscosity that makes it difficult to transport in pipelines. For this reason, it is necessary to reduce the viscosity of the crude oil by mixing it with light hydrocarbons or polar solvents. But how can this substance decrease the viscosity of crude oil? First of all, it is important to understand that the viscosity resulting from the mixture depends only on the dilution rate and on the viscosities and densities of the oil and the diluent. In the case of light hydrocarbons, we want them to have low densities and a lower viscosity than the crude, so that due to the effect of the combination of components, the resulting viscosity of the mixture is lower than the initial one from the crude. On the other hand, the addition of a polar solvent to a solution with asphaltenes acts on the colloidal structure of the asphaltenes, reducing the relative viscosity of the solution. However, polar solvents that have few hydrogen bonds give a significant reduction in the absolute viscosity of the diluted crude, and polar solvents with high hydrogen bonding are more viscous than hydrocarbons, and its interaction with asphaltenes are not appreciable in terms of absolute viscosity. Now, having cleared the importance of reducing the viscosity of crude oil with solvents and its theoretical foundation, we are going to move up to the objective of the practice carried out, which is analyze the viscoreductive effect of acetone and toluene in crude oil. Now we are going to present the methodology used in this practice. First, we add 30 milliliters of crude in a beaker. Then we add 5%, 10%, 15%, or 20% solvent of the total volume of crude depending on the sample we are going to do. Then we mix the crude oil with the solvent until an homogeneous mixture is observed. Now we move on to the rheometer, which is the laboratory device that we use to measure the viscosity. First, we have to turn on and prepare the rheometer, then place the coaxial cylindrical geometry, and then add 25 milliliters of the sample to the glass of the rheometer. After that, we lower the geometry to get a 5 millimeter gap. Then we select the method we want to use, in this case, steady state flow with a shear range between 1 and 100 with 5 steps and a temperature of 20 degrees Celsius. Finally, we lower the plate and press play.
With the procedure mentioned before, we obtained the following results. Thanks to the rheometer, we were able to obtain this table with the information about the crude oil sample. And the most interesting information is given by the shear rate, the shear stress, and the viscosity in pascals per second. Also, we can see on the right side of the screen the sample of crude oil before any additions. In order to understand better the results given by the rheometer, these were organized in graphs in MATLAB. The one on the left shows the shear stress versus the shear rate for crude oil, and it can be seen that there is an increase in the shear stress as the shear rate increases. The graph on the right shows the viscosity against the shear rate, and it can be affirmed that the viscosity for crude oil is very high and that it decreases as the shear rate increases. In the case of the sample of crude oil with acetone at 10%, we obtained this table with the rheometer. We can also see in the video how the consistency of the sample changed by adding this 10% acetone. In this case, the graph of shear stress versus shear rate also shows that the shear stress increases as the shear rate increases. However, in this case, the shear rate range is greater than in the crude oil case. Also, in the graph of viscosity, it shows a reduction in viscosity compared to the graph showed for the crude oil. These results will be explained in detail in the analysis.
Now we will move on into the analysis and discussion. As seen on the graph related to the shear stress versus the shear rate, the fluids we are working with are Newtonian. This is because their behavior is linear. This means that their viscosity is constant and will only be affected by temperature. It is also evidence that through the addition of acetone of 10%, the viscosity did decrease. This can be seen through the graph because it was faster to reach a certain amount of shear stress in acetone than in the crude oil. This shows that the crude oil cannot be manipulated effectively. This is what creates issues in the industry. In a molecular point of view, this shows that the shear stress that is applied to the oil does not affect the bonds of the asphaltenes. Now, when we add the acetone, it is seen that it will create an easier manipulation of the oil and will most likely debilitate the bonds of the asphaltenes. The impact of the reduction of viscosity by adding acetone is seen in the graph. There is a significant decrease of viscosity by adding this polar solvent. This is shown because in comparison to the crude oil, there is a decrease of approximately 10 pascals by second of viscosity. Acetone is a polar dissolvent that works correctly to debilitate the forces that are present in the asphaltenes. It was possible to see an accurate comparison of the different solvents used and their concentration. In terms of the acetone at 10%, it was possible to reduce the viscosity, but it is recommendable to use it at higher concentrations. Because at higher concentrations of acetone, there are more polar molecules in the crude oil. The forces regarding the asphaltenes will debilitate and the viscosity will decrease. But now, in terms of which is the most effective solvent that will successfully decrease the viscosity of the crude oil, it is seen that toluene at 15% is the better choice. In comparison to acetone, toluene is more polar and doesn't form hydrogen bonds. This gives a significant reduction to the viscosity of the crude oil. The bonds of the asphaltene will be less strong and the crude oil will be easier to manipulate and transport. Because the acetone can form hydrogen bonds and is less polar, it becomes a second choice when deciding to reduce the viscosity. After pouring the solvent in the crude oil, the decrease in viscosity was immediate. This was intriguing to see. For future projects, it will be interesting to accurately depict the impact the temperature has on viscosity and how this will look physically. With everything presented before, here are our conclusions. In conclusion, it is evident that adding organic solvents to crude oil is extremely important in industrial terms. This is because it helps to reduce the viscosity, and because of this product can be transported and its movement can be facilitated through a pipeline. Additionally, it was seen how the crude oil and its mixture with solvents had the behavior of a Newtonian fluid. In terms of which solvent was better, it was seen that the solvent, being more polar, more concentrated, and without hydrogen bonds, was able to decrease the viscosity successfully. In this case, this solvent corresponded to toluene at 15%. On the other hand, acetone was able to decrease the viscosity, but it wasn't better because it could create hydrogen bonds, and this does not debilitate the forces that are present in the asphaltenes.